So let's look at one example on how to use conservation of energy. So the problem we have here is a boy that is going to go down the slide, and we want to study this problem and find how much energy, how much thermal energy is dissipated. So Quinn is at rest at the top of a playground slide. So the main part of the slide is 5 meters long. So you have 5 meters there, and it is tipped at an angle of 30 degrees. So Queen starts sliding, moving down, and then so at the end it has a speed of 2 meters per second horizontally. So Queen is 24 kilograms, and the question is how much thermal energy is released, is deposited, how much does he heat up as he goes down the slide. So a picture of the whole thing is this. Queen is here initially, the initial velocity is 0, and then it comes down the slide, the final velocity is 2 meters per second. So as it goes down, so you have h here, that's the height of the slide, and this is 5 meters, is this length here. These are two different lengths. And so we want to find out how much thermal energy it is released. So let's write our equation. So we have, so the initial energy, right? So the initial energy have to be equal to the final energy plus whatever energy I lose as heat, right? So that is what is written here, right? So initial energy, which, what is that? Is the energy of motion, which is 0 because it's not moving, and the potential energy, which is mgh, right? So that is the potential energy, is equal to final energy. What is that? That is 1/2 mvf squared, and then that is the energy of motion here, right? And then the potential energy, which is 0 because, well, this is 0 right here, right? So from this, now we can solve for this delta energy and solve for the problem. So we can find h by using the length of the slide and some trigonometry, that's 2.5 meters. And then we can solve for delta ETH, which is the thermal energy. And so that is equal to the potential energy at the beginning minus the kinetic energy of motion at the end. So we plug in the numbers and we find that that is 540 joules that are dissipated as heat as this goes down the slide. So let's look at, again, review the terms in these equations. We have energy of motion, kinetic energy, we have gravitational potential energy, we have elastic potential energy, right? So those are the three of the main three contributions to energy. We have work, and then our equation is this, right? So let me write it this way first. The energy that you have initially plus whatever you put in or take out through work have to be equal to the energy that you end up with plus whatever you lose through heat. That is your equation. That is here. And what is this? This is kinetic plus potential. And this is also kinetic plus potential. Sorry, kinetic plus potential. So that is our main equation here that we're going to use to solve to solve problems in this section of the course. So let's look at energy diagrams. One way that we can visualize the energy is to plot the total energy here and the position here, right? So, and then we can plot different types of energy. For instance, if we were to plot the elastic potential energy, it would be a parabola like this. If we were to plot this is the gravitational potential energy, then it will be a straight line in a plot like this. So these energy diagrams are useful to understand what the system is going to do. For instance, let's say we have a mass attached to a spring, right? So this is going to oscillate back and forth. So it's going to go from here to here, back and forth, right? So this point here, this is an equilibrium point. So if the mass would like to stay there forever without motion if you don't do anything. So, and it's going to oscillate back and forth around that point. So that is how we use and read uh, energy diagrams. So here is a more complicated energy diagram. Let's look at some points. If you start here, imagine like this is kind of a roller coaster, right? If you start here, you're going to speed up. When you go up here, you're going to slow down. When you get here, you slow down the most, and then you're going to speed up again. And then you're going to slow down. And if there is no energy loss, you're going to come back up here, right? So these points have names. This is equilibrium point. These are equilibrium points. This is a point of stable equilibrium. The particle would try to be there forever. This is a point of unstable equilibrium. If you move this, if the particle is there, initially it's going to stay there, but if you touch it a little bit, it's just going to fall and come back down to this point here. This point here is a turning point. As soon as the particle gets here, it's going to go back down, and so it's going to turn around. So these are called local minimums. Those are stable equilibrium, and this point is a local maximum and is an unstable equilibrium. So one more thing that we need to look at is energy in collisions. So we have two types of collisions that we're going to study along with energy in elastic and inelastic collisions. In an elastic collision, energy is conserved, you don't lose anything. In an inelastic collision, you lose some energy, being through sound, through other stuff. So in this problem here, right, so let's look at this typical problem. You have two trains are coming at each other, they collide and they get stuck, right? So these are initial velocities. This is final velocities. You're given the masses of the train, and conservation of momentum applies here, right? So we have conservation of momentum. But what happens to the energy? Well, we're going to have initial energy, final energy, and some energy that you're going to lose as heat because of the collision, right? So then we want to write the kinetic energy, which is the kinetic energy of motion of the two trains, right? So that gives me 4.7 times 10 to the 4 joules. The final kinetic energy is the energy of motion of the two trains when they are stuck together. That's why we have the mass here. That gives me 1900 joules. And then from there, I can solve for the energy that is released as heat, which is the difference between what I had at the beginning and what I end up with. So that's my heat energy, and that is this much here. So this much energy is released as heat after the collision or during the collision. So elastic collisions, on the other hand, they conserve energy, right? So the energy that you have at the beginning equals the energy that you have at the end, so you get this equation here. So, and in this case, it's all energy of motion. In the collisions that we're going to consider, we're not going to consider any potential energy. So this is a second equation that you can use to help you solve problems in some cases. So if we were to work with these equations and do some manipulation, then you get these equations for the final velocities in elastic collision. So now we have two equations along with the conservation of momentum equations that we can use to study problems. So let's just look at two hockey pucks, right? So we have one at 0 and the other one coming at this with velocity, initial velocity, and then at the end you get two velocities. So you have two unknowns here, right? And then you have this other thing here that you know, right? So then how do we solve this? Well, we use these equations for energy. So we have the initial velocity, the final velocity of puck 1, the final velocity of puck 2. This is going to be 0 because it's the same masses, and this is going to be twice because it's twice the initial velocity. So basically what this does, if you look at this guy was coming at this as 2.3 meters per second. This is at 0, so this is gonna collide here. This is gonna stay put here, right? And the other one is gonna just go. And the velocity of the second one is gonna be 2.3 meters per second.